Okay, so at this point, you should be very familiar with chemical reaction, right? You guys did one last week. So one way that we determine that there's chemical reactions is if whether we see a color change, if we see a product, a solid product being produced, the formation of a gas product, heat being absorbed, heat being released, or light being emitted. So when you guys did the experiment with the balloons, what happened?
Gas was formed.
You made gas, right? You got real gassy, right? Yes, no, maybe?
Yep.
Okay. So in the case of the glow stick, what happened in that case? Didn't you guys do an experiment with the glow stick?
Yes.
Yes.
Light was released or light was created.
Light was created. Okay, so light was emitted. Okay. So those are examples of chemical reactions. That's evidence of chemical reaction. And so often we'll sit there and see it. We'll see that color change. We'll see solid being formed. So this is an example of precipitation. When two things come together, when they form a solid, they precipitate out. So they'll make like a cloudy structure. And if we let that cloudy structure sit long enough, it'll drop to the bottom. That's called precipitation. So that lets us know that there's a solid being formed. Or we have gas, gas formation. We could have heat and light being generated, or we could have light being emitted. Or we can even have the case where we're making coal. So you don't have to necessarily make heat. You could be sitting there making coal, right? So heat is being transferred from the outside into that reaction. And so it's causing the environment to be colder. So here we have this reaction. Sodium is reacting with water. So when solid sodium is added to liquid water, the reaction occurs producing hydrogen gas and sodium hydroxide solution and heat. So you guys are now experienced. Can you tell me the chemical equation that we're going to be writing in this case?
We would start with Na.
Okay. Is it a solid, liquid, or gas?
Would it be solid?
So we're going to put an S here for solid. Okay. What else is it reacting with?
Water.
So is water a solid, liquid, or gas?
Liquid.
Okay, so we're going to put a little L and parentheses down here. And then that's going to make
NaOH.
and
H2.
that's right, H2. Good job. You remembered that it was diatomic. So is that a solid, liquid, or gas?
Gas.
And that sodium hydroxide is a solution. So anytime that you see a solution, that basically means that it's going to be in water, unless they tell you otherwise. Okay, so then you would put aqueous for being in water. That's right. Okay, piece of cake. Now, is it balanced? That's right, it isn't balanced. So we need to balance it. So what am I going to do to balance it? Oh, by the way, Nate, where were you on Tuesday?
I was in the emergency room. I had a kidney stone forming.
Oh, really? Sorry.
No, it's all right. It hurt like a crazy. I woke up at like 3 a.m. and I was like dying. I went to the emergency room. I was there for like 5 hours. So I was asleep during class, to be honest.
Okay.
A rough day.
I've had those, believe me.
Yeah, it still hasn't passed, so I'm looking forward to the fun part. But
Oh, that is going to be
yeah,
fun.
we'll see what happens. Maybe it'll go away. I'm
Did
drinking.
did they tell you drink a lot of liquids? Yep.
Orange juice.
Yes. Because of the acidity, right?
Yeah, exactly. You want to do a chemistry analysis on that, but
Yeah. Because I believe it's calcium carbonate or calcium. It's calcium something.
it's a calcium buildup in the kidney or whatever because it's not flushing enough.
Yeah, but it forms a precipitant, and so it's precipitating. It's aggregating together, and it gets bigger and bigger and
Then it moves through.
pointier and pointier.
Yeah, exactly. It's like a little crystal, basically.
That's right, because you're forming crystals.
Yeah, I'm not looking forward to it. It's my first time.
Yep.
But anyway, sorry.
Okay, so is this balanced?
Nope.
No.
Okay, so what do I need to do what do I need to do to balance
Write down our elements.
it? Okay, so let's see. What do we have here? We have sodium,
H.
and I heard a H and an O.
Yeah.
Okay. Okay, on the right-hand side, how many sodium do we have?
1.
And on the product side,
1.
1.
on the reactant side, how many hydrogens do we have?
2.
And on the product side,
2. 3.
how many oxygens on the reactant side?
1.
And on the product side?
1.
Okay, is that balanced?
No.
No. Okay, so what do we need to do to balance it?
3. I mean,
Put it.
6.
Okay.
Would you put a 3?
Put a 3? Where would I put a 3?
In front of
There
the
is a-
H2O?
You said 3 in front of the H2O?
6.
You said a 6 in front of the H2O.
I said a 6.
Okay. Why would you put a 6 there? We'll do it just to see what happens. Okay, so now I have 12. So is 12 equal to 3?
No.
No, so that's not getting me any closer to 3 by putting a 6 there. So we're not going to pick numbers at random, really, are we?
No.
Oh, we can. I mean, I've seen people do it, and it can work. Okay, but let's look at this, right? So we have 2 here, we have 1 here. So we have a total of 3, right? Is there any way that I can make this, since we know that this is a 2 over here, and this is my only source of hydrogen, is there any way that I can make this a 4 or a, like you said, a 6 on this side of the equation? So then I could just put a whole number on that side of the equation.
Would we put in a fraction?
Is it a 3 on the product,
If,
on the
if, you,
reactant?
if you put in 2 in front of the sodium hydroxide, that makes
Okay.
it 4 hydrogens.
So if I put a 2 here, that gives me an even hydrogen, right? And we know that this guy has 2 hydrogens. This is my only source of hydrogen. And it has multiples of 2. So I'm going to try to make sure I have multiples of 2. So that kind of makes sense, doesn't it? So now I have a total of 4 over here. So then if I have 4 over here, how can I make it so that I have 4 on my reactant side?
Add a 2 to the water.
Okay, so if I add 2 to the water, I now have 4 hydrogens. It's balanced on both sides. Now my oxygens, are they balanced on both sides?
No.
Yes.
Oh, yeah.
Yes.
So now,
Yes.
Oh, no, not number.
are you sure? Because we have 2 here, and now we have 2 over here, right? So it's balanced on both sides. Now what about my sodium?
No.
No, because I have 2 over here. So I need to put what in front of this sodium?
2.
Okay. So now is it balanced?
Yes.
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 Okay, again, bread and butter of chemistry. Got to be able to balance equations. That's why we started at the very beginning. We're about what, 4 weeks, 3 weeks out? 3 weeks out before classes are over. So we got to make sure that we know how to balance equations.
Dr. Henry, I was about to say, put a do it in front of NA.
Do it.
Do it.
What is
That's
a do it?
Italian.
Okay. I'm learning something new every day. Okay, so that's that process of balancing chemical equation, right? And so the idea is that we want to make sure that the equation is balanced. There are a couple of things that we want to be sure of. Let's talk about those couple of things. Okay, first off, you want to be familiar with all of the symbols. You need to know that S stands for solid, L stands for liquid, G stands for gas, and AQ stands for aqueous, which means it's dissolved in water. The do's and don'ts of balancing equations. You always want to make sure that your chemical formulas are correct, right? So if your chemical formulas are wrong, then you're not going to be able to get the right coefficients in front of them. And so you're going to use coefficients to balance the equations. You're not going to change the chemical formula, right? You're also not going to make up chemicals, right? Either or throw in chemicals, real or imaginary, just to try to make things balanced, okay? Not at this point. Okay, are you guys with me so far?
Yes.
Yes.
Kind of like the same thing your mom told you, right? When you were growing up, you know, don't make stuff up, you know, otherwise you're gonna get a butt whooping, right? Because that's the same thing that happens with balancing chemical equations. Don't make stuff up, otherwise you're gonna get a butt whooping. Did your mom tell you that growing up? No, my mom did. Okay, so you always want to sit there and make sure your chemical formulas are right. You want to make sure your reactants are on the reactant side of the equation, and then your products are on the product side of the equation. Okay. Are you good so far?
Right.
Okay. And then I always like to make sure things adds up. I am a little slower than other people, so I write the things in the middle, all the elements, and then I make sure that my numbers add up, because that lets you know if you're right or wrong. And then, like, I noticed, like, the very first time that you guys balance equations, some of you guys were giving me some crazy answers. And some of you guys didn't even put in the numbers. You were writing in crazy things. I didn't even know what you were writing. So that let me know that some of you guys actually paid attention to lecture. Well, you at least were putting in numbers. And then some of you guys really paid attention to lecture because you took the time to balance it. So I looked over your sheets, and believe it or not, I do go through all that crap. I look over it all, right, to try to sit there and find points for you. So sometimes I'll notice, hey, you got it right on your paper, but you wrote down the wrong thing. And so I'll end up giving you points that way.
Is that for the test? Is that what you're talking about?
Yeah, yep. So all your tests, you guys have had balancing chemical equations since the very first test. You've been
I
doing
know they're the ones that I spend like 30 minutes cussing about because I can't get it to add up correctly.
Yeah.
That's all right. You got to keep doing it until you do it, right?
I
Then you'll
paid
get it down
like
to just
3 pages of equations crossed out until I finally get to the answer.
Okay, so balance the equation for the reaction of solid phosphorus, pentachloride, and liquid water, yielding aqueous solutions of phosphoric acid and hydrochloric acid. Okay, so what is the chemical formula?
PCl, no. P- PCl5.
Cl5. Is that a solid, liquid, or gas?
Liquid.
Solid.
Solid.
Plus
H2O.
Liquid. That's a liquid.
Are you sure? Are you sure, Nate?
Yeah,
Yes.
1 point for me. I said it first.
And we're gonna make
H. 3.
Come on. I know you can get it. I know it's there.
SO4.
PO3.
Oh,
Is it 03?
PO4.
04.
Oh, 4. Sorry.
See, Catherine did all the hard work, you know,
Plus CL. HCl.
plus HCl. And what is the state for
AQ.
AQ? That's right. Oops.
HCl.
And that's AQ.
Yes.
Okay. Is it balanced?
No.
Okay. What do we need to do?
Balance it.
Balance it. So we have an H, we have a P, we have an O, and we have a Cl. Okay. On the reactant side, how many hydrogens do I have?
2.
On the product side,
4.
on the reactant side, how many phosphorus do I have?
1.
And on the product side,
1.
on the reactant side, how many oxygens do I have?
1.
And on the product side,
4.
4.
on the reactant side, how many chlorines do I have?
5.
5.
And on the product side,
1.
okay? So let's do this. Are we balanced?
No.
Okay, what do we need to do?
Balance hydrogen first.
Okay, so let's balance hydrogen first.
You put a.
So we're-
Oh, go ahead.
Okay,
I was just gonna say put a 4 in front of H2O maybe.
I
four in
would,
front of four in
I
front
would
of
say
H2O.
2. A 2.
It's gonna
two?
have to be 4 eventually to match the oxygen. So
Because the chlorine and the hydrogen on the other side is gonna need a, let's see, we have to get 8, or the chlorine we need 5 more. So you gotta put 5H, 5 in front of the HCl on the right side.
Okay,
Let me see. That's all I got so far. I'm still looking at it. I'm trying to count.
okay, so then that gives me how many chlorine on the
5
product side? 5. And then
8,
how many hydrogens?
8.
8. Okay, so if we put that 4 in front, that means that we have 8 here.
Okay.
And then how many oxygens?
4.
4.
Ooh, I did it. Edgar, that's in your face, son. I don't even think he's here.
no, I'm here.
In your
Do
face.
you like the competition, Edgar?
I'm just sitting back.
He already had it done, probably.
Okay. Pretty good, simple.
For
And
this,
so if you guys have done that lab, you know, the lab, I guess lab 8, I think it was lab 8, lab 7 or lab 8, I can't remember which one. You had a lot of practice, right? So you guys are professionals.
If that was on the test, I would not have been able to get it.
Why not?
I would have, I don't know, I just would have struggled for like 30 minutes. I don't know why. It just came to me right now like a vision. But when I'm in front of the test screen, I can't do it.
We always forget in front of the test.
Because the proctor is staring at me. I'm thinking about moving my eyeballs too much.
Okay, so when we talk about chemical equations, we talk about it, a lot of times we talk about it in the particulate level. That basically means like molecules. So 2 molecules of hydrogen gas plus 1 molecule of oxygen gas is going to make 2 molecules of hydrogen, right? So in that case, you're not going to have a half of a molecule, right? But on the molar level, you guys remember moles, moles is huge, right? We can have a half of a mole and still have like a lot of those molecules, right? And so we can sit there and have that half of equations in the case on a molar level, but not on a particulate level. And since we don't know how things are going to be used generally, we always like to have it set up on that particulate level to make it easier for whoever's doing the work after us. So when our boss takes a look at our work, they can see that, oh yeah, I took that time to get rid of that half. in that equation, right?
Dr. Henry, can I ask a question real quick?
Yes, you can, sir.
On the homework, I was having trouble with the molecules to mole relationship. Is it that there's 6.022 times 10 to the 23 molecules in 1 mole?
That is correct.
Okay.
Yeah. So
Thank you.
like a mole is like the equivalent of a dozen, right? Because a dozen means 12, but a
Right.
mole means 6.022 times 10 to the 23.
Well, a molecule would be each egg in a
Yes,
dozen.
that's right. So
Okay.
a molecule is like an egg. Yes, that is
Alright.
correct.
Thank you. I was just trying to convert everything and the relationship was confusing me.
Yeah, it's funny because when you said that, when I was in chemistry in high school, I would always mistake a mole for a molecule because I thought it was just the abbreviation for it.
That's what I was having
Right.
trouble with in the conversion charts.
Yeah.
Like you have to put one on top and one on the bottom, and I was like confused about the relationship.
Yeah, and that's the thing about chemistry. You'll notice that we use a lot of the same symbols over and over and over again. And so sometimes you can kind of get confused in it if you're not paying attention, right? Or you make assumptions. A mole, you say, oh, it's a mole, right? You're thinking molecule. They're not the same. Okay, so this is just basically showing you what we talked about. So this is a dozen, right? So here we have 2 dozen of hydrogen molecules. We have 1 dozen of oxygen molecules. And that's going to make 2 dozen of, of water. Okay, so it keeps that mole, it keeps that ratio, right? So that quantitative ratio with each other. So that chemical equation is always going to represent that quantitative ratio. Right? So, okay, so let's talk about types of reactions. So this reaction where you have A and X coming together to make AX, that's going to be a synthesis reaction, or we call it a combination reaction. So 2 or more things coming together to make a single product, combination reaction. Okay, here's an example. Write the equation for the combination of solid aluminum and gaseous oxygen form solid aluminum oxide. Okay, what is the chemical equation for this?
Al subscript S.
Plus O2.
Okay,
Subscript G.
and what are we making?
Al2O3.
O3.
Subscript S.
Okay, are we done?
No.
What is the next thing that we have to do?
We need to balance.
We need to balance. Okay, so what do I do to balance it?
List the common elements.
Okay, so I have 2, 3, 1, 2. Is it balanced?
No.
No.
Okay, so how can I start balancing?
You can add a 2
Two.
from
First, balance the Al2O3 because that makes it easier. So
Okay.
add a 2 in front of it.
Okay, so then that gives me 4 aluminum and 6 oxygens.
then you can add a 3 in front of oxygen. Yeah, 3.
Okay, so then that gives me 6 oxygens.
And a
You add a 4
4.
in front of aluminum.
Okay, so that's balanced, right? Piece of cake.
Yes.
Good. Let's move on. Okay, so our next reaction is called a decomposition reaction. Decomposition is just breaking down things, right? So we have AX being broken down to A plus X, decomposition. Okay, so here we have water decomposing into its elements when electrical energy is added. Write the equation.
Does it start off with H2O?
Okay. Solid, liquid, or gas?
Liquid.
And it's going to make
H.
H2.
And O.
and just O,
O2.
O2. So why are those twos? Why don't I just put H and plus O?
They are diatomic elements.
Because they're diatomic elements. That's good. Have no fear of ice cold beer. Good job. Am I missing anything?
Yeah.
Their state.
Okay, what state are they?
Gas.
Yes.
Gas. Okay, is it balanced? Am I done? Can I
No.
have my beer?
No.
No? Okay, what do I need to do?
Write the elements.
Okay.
There's two hydrogens and two,
Okay,
and 1 and 2.
okay, so what do I need to do now?
Add a 2 in front of hydrogen and the reactant side.
Okay, in front of the water.
Yes.
Okay.
And then add a 2 in front of the other hydrogen and the product side.
And the hydrogen gas. Okay, are we balanced now?
Yes.
Yes.
Good. It's so good to hear different voices. Don't get me wrong, I like Edgar and Alan, but and
Neat.
Nate. Okay, so now some reactions are reversible. When we have a double arrow like this, then that indicates that the reaction is reversible, meaning it can go both ways. Okay, so it can go and we can make the gases, or we could be making the liquid. So it can go both directions. Okay, and there's a point where certain reactions, they get to a point that they form what we call equilibrium. So you have both states, you have your products existing and your reactants existing in the same tube. And they're existing in the same, or I should say at an equal, like at an equal, well, it's an equilibrium. So that they're kind of like equal, but not quite equal. And I'll kind of explain that when we get into equilibrium, okay? But it's just the fact that you have both states existing at the same time. And so you're making, in this case, you'd be making water at the same time that you're making the gases. And that rate of making water and making the gases are going to be the same rate, okay? So nobody's going to be favored. Okay, so this is called the single replacement reaction. It's also sometimes called the oxidation reduction reaction or redox reactions, okay? So here we're replacing B with A. And A and B have to be similar, like they have to be metals, right? They both have to be metals. Or they both have to be non-metals to be able to replace each other, okay? You guys get that?
So they're
Okay.
basically
Yes.
like switching.
Yep. So it's kind of like, you know, you're dumping the old girlfriend for the new girlfriend or boyfriend, okay? Boy, nobody laughs at my jokes anymore. God, it must be not funny. Okay, so like I said earlier, when we're replacing those elements, the metal can only replace a metal or hydrogen, because hydrogen can kind of act like that metal sometimes, right? or nonmetals have to replace nonmetals. Okay, let's test your skills out here. Copper reacts with a solution of silver nitrate. Write the chemical reaction. Okay, so what are we going to do?
Write out the equation.
Okay, so what is my equation?
Cu.
Solid, liquid, or gas?
Solid.
Good job, Sal. Cu plus
Ag.
Ag.
and 2.
Are you sure it's N2?
NO2.
Are you sure it's NO2?
NO3.
NO3.
NO3. Okay. Is
Oh,
it
I
a
got them
solid,
mixed up.
liquid, gas, or aqueous?
The
It's aqueous. That's right, because it says solution. Okay. And what am I going to make? What is going to be the product?
Cu NO3.
Okay. So I'm going to tell you guys something, and I want you to keep this in mind, and we'll talk about it again here in about an hour or so, or in a few minutes or so. So anytime that you have a transitional metal other than silver, and you're replacing it with something, that transitional metal almost 90% of the time, 99.9% of the time, except for silver, is going to have a +2 charge. So if copper is going to have a +2 charge, how many nitrates am I going to need to balance it out?
2.
Okay. Okay, and what else am I going to have?
Ag.
Ag. Solid, liquid, or gas?
Solid.
And then what about the copper nitrate?
AQ.
That's right. So if there's no precipitant, usually your reaction says you get a precipitant. Precipitant basically means that you have a solid. That means that if they said that there was going to be a precipitant, it will be a solid. Otherwise, assume that it's going to be an aqueous solution. Okay? Because you started out with an aqueous solution. Okay, you got all those little tips down, right? Because those tips are going to be important.
Can you repeat it? Actually, you said I missed the first part. Said
Sure.
for silver, it has a +2 charge. What was the first part?
I said, anytime that you have a replacement reaction, all metals, when they're being replaced, by something else, or you say you have that metal and it's going to go into this other reaction, right? It's going to have a +2 charge. Almost all metals are going to have a +2 charge, except for silver and aluminum. As we know, aluminum is always going to be +3, and silver is almost 99.99999% of the time going to be +1.
Got it. Thank you.
Okay, but everything else, for some reason, it just works out that way. Almost all the time, it's a +2 charge. Okay, so the next type of reaction that we have, oops, I don't know what happened. Okay, next type of reaction that we have is it's a double replacement reaction. Double replacement, it's also called a double displacement reaction. Sometimes they'll call it a precipitation reaction. So in a double replacement reaction, you're replacing the partners. So A is going to partner up with Y now, and B is going to partner up with X. So it's kind of like a swingers party, right? So you're going to be switching partners. So then you're going to end up with AY and BX. Okay, you guys got that?
Yes.
Yes.
So let's test out those skills. Silver chloride precipitates when a solution of sodium chloride and silver nitrate are combined. write the chemical equation for the reaction. Silver chloride precipitates when solutions of sodium chloride and silver nitrate combines. Write the equation for the reaction. Okay, so what is it going to be? Finally, somebody laughed.
NaCl, aqueous,
NaCl.
aqueous,
Okay.
plus AgNO3.
Solid, liquid, or gas?
Aqueous.
Or- okay. And what are we going to make?
Yields AgCl, solid, plus NaNO3.
Okay, so what did you say solid for AgCl?
The question states it precipitates.
Excellent, good job. Okay, is it balanced?
Looks like it.
Yep, it's balanced. Piece of cake?
Piece of cake.
I have a question, Dr. Henry.
Yes, Helen.
Why did you put first nitrogen, sodium chlorate instead of silver chlorate?
Because the question says, if you read the question, it says silver chloride precipitates when solutions of sodium chloride and silver nitrates are combined. So these guys are going to be my reactants, because the only way that this guy is made is by these guys coming together. So these guys are going to be the reactants. Right?
Oh, okay.
So you want to make sure to read the question. And sometimes I think they word it that way because, you know, normally the way we think is, it's like, oh, if it's in front, that's going to be our reactant. Sometimes they word it differently to kind of keep you on your toes, so you don't get in the habit of just being a little lazy and not, oh, I'm just going to, those are in front and I'm just going to write those down. And I noticed that they do that on a lot of your standardized tests as well. Okay. Okay, the next type of reaction are kind of specialized reactions. So this is called the neutralization reaction. It's also called the acid-base reaction. So we've kind of talked about acids and bases. We're going to talk about them a little bit more. Hopefully we'll play with a little bit of acids and bases towards the end. Not the good kind. So in terms of acids and bases, an acid is basically a proton donor. It's an H+, right? And we know that's a proton because hydrogen, the hydrogen ion, or the hydronium ion, it has only a proton. You don't have any electrons in the case of that. You're already giving it away. And you don't have any neutrons, okay? So acids are considered proton donors and bases are considered proton acceptors. Okay, so that basically tells you what's going to be happening in terms of this reaction. So in this case, we have the acid is kind of generically written as HX, and then our base is written as MOH. So the hydrogen from the acid is going to be donated to the base. And these guys are going to come together. Now, if we think about this to form water, if we think about this, this is just our double replacement reaction. It's just a special case of the double replacement reaction, okay? Because then all you're doing is switching partners. Your X is going to meet up with your M, right? To form your MX. Okay, so when you have an acid and base reacting together, you're going to end up with water and a salt. Okay, are you with me?
Yes.
Good. Okay, so write the equation for the reaction between sulfuric acid and solid aluminum hydroxide.
H2SO4 aqueous plus Al parentheses OH close parentheses 3 yields.
Is it solid, liquid, or gas?
Oh, solid. H2O
Solid, liquid, or gas?
liquid plus Al, and I haven't done this yet. Al2S3 solid.
S3?
Mm,
So
Yeah.
4
SO4.
parentheses
Ah.
3.
Parentheses 3. That's right.
okay.
Okay. Solid, liquid, gas, or aqueous?
Solid. No, never mind then.
Aqueous, AQ.
AQ. Okay, it's going to be aqueous unless they state that it's going to be a precipitate. Okay, so that's kind of a hint. And then you guys, because particularly right now, you guys haven't talked about solubility. We're getting there. Okay, so is this balanced?
No.
No. Okay, what do I need to do to balance it?
List the common elements. You can just keep SO4 as it is.
Okay.
Aluminum and then SO4.
Okay. So on the product side, how many aluminum do I have?
2.
On the reactant side,
1.
how many SO4s do I have on the reactant side?
1.
And on the product side,
3.
how many oxygens do I have on the reactant side?
3.
And on the product side,
1.
and how many hydrogens do I have?
5.
And on the product side,
2.
okay, is it balanced?
No.
Okay, what do I need to do? Start with that aluminum. So how can I make it so that I have 2 aluminum? How can I make it so that the aluminums are balanced?
Put a 2 on the reactants.
Okay, in front of the aluminum hydroxide. So then that gives me 2 of these guys, 2 of those guys, and then that gives me how many? How many H's here?
8.
Okay. And how many oxygens?
6.
Okay. Now what about the sulfurs? How can I make it so that I have a balanced sulfur?
3 in front of the sulfuric acid.
Sulfate, not sulfur. So put a 3. Okay, so then that's going to change my hydrogens to how many hydrogens now?
12.
Okay, now what about my oxygens? How can I get my oxygens balanced?
Oh, you can add a 6 in front of hydrogen in the product side, so that will balance your hydrogens and oxygens.
Okay, so that's going to give me 12 and 6. Okay, so if you do it this way, you got to be careful not to double dip on the oxygens, since you have oxygens here and you have oxygens here. So you want to make sure you keep that clear. Okay, but it's balanced, right? Yes, no, maybe?
Yes.
Yes.
Okay. Okay, so in summary, in summary, these are your type of reactions. You guys are very familiar with them. There's also one other reaction that I want to talk to you guys about it real quick, and that's a combustion reaction. And typically when you have a hydrocarbon, C6, C2H6 plus oxygen is going to yield carbon dioxide and water. Okay, so anytime that you see a combustion reactions with a hydrocarbon, you're going to get carbon dioxide and water. You can also get combustion reactions with sulfur. And so in both cases, you're going to need oxygen. Oxygen is required for you to maintain that fire. To have combustion, you're going to have oxygen. So it's always understood. So anytime that you see a hydrocarbon burning is burning, what's going to be produced? You know you're going to have oxygen. It's going to be provided by the air, and you're going to be making carbon dioxide and water. You guys got that?
Yes.
Yes.
Okay. The only thing, you got to make sure to balance it out. So how would I balance this out?
List C, H, and O.
Okay. How many carbons do I have on the product side?
1,
On the reactant side?
2,
How many hydrogens do I have on the reactant side?
6,
And on the product side?
2,
How many oxygens do I have on the reactant side?
2,
2,
And on the product side?
3.
Okay, is it balanced?
No.
Okay, what do I need to do to balance it?
2 CO2.
Okay, so then that gives me okay, is it balanced?
Not yet. 3 H2O.
Is it balanced?
No, I think we are missing something.
We're missing something. Can I do this?
On the reactant, yeah. Fraction.
Then multiply both sides by 2. You guys remember doing this? So then I get oops. Okay, piece of cake. Pudding pie.
Piece of cake.
Good. So let me clear. Okay, so when we're conducting electricity, right? Electricity is just the movement of electrons through the electrodes, through the metal, right? So electrons are basically flowing through here, and if these two pieces of metal, these electrodes are touching each other, the electrons are able to flow through, and then we're able to get light. That's how light works. So if I click that switch, it basically puts a gap between the two electrodes, and then I don't get any light. Make sense?
Dr. Henry, can you make that full screen?
Was it not full screen? Oh, I'm sorry.
No.
That's my little screen.
Yeah.
Can you see it now?
Mhm.
Okay. So electrolytes are basically charged particles, right? So non-electrolytes don't have charge associated with it. So like example, ethanol doesn't have a charge associated with it, right? It's neutral. So it's not able to conduct electricity. Water is not able to conduct electricity, okay? So you're not gonna get light being able to flow through water or through ethanol. Now, your ions, when your ions in solution, when your ions are in an aqueous solution, your ions separate. So you get your charge, right? So for instance, copper to chloride, you're gonna have, copper is gonna be 2+, your chloride is gonna be minus. So in solution, you're gonna have your 2+, and you're also gonna have your minuses in solution, okay? So you're gonna have your minus charges and your plus charges. Because you have those charges, you're able to sit there and conduct electricity because they keep that electricity flowing, okay? I mean, the electrons flowing, okay? So strong electrolytes, when they totally dissociate, the way that we distinguish between a strong electrolyte means that you get total dissociation, meaning that you have all your, or the majority of your particles are separated into the charges, where a weak electrolyte, only some of them dissociate into their charges. So for instance, acetic acid is considered to be a weak acid as well as a weak electrolyte. The reason why it's considered a weak acid because the acetate and the hydronium ion don't dissociate a lot. You only have a little bit of them in solution. If you kind of take a look here, you'll see you have 1 plus charge and 1 minus charge, where here you'd had a whole bunch of pluses and a whole bunch of minuses in solution. This one only has that 1. But if you take a look, it stays together the majority of the time, right? And so that means that that hydrogen isn't coming off readily, right? Making it weak. And so because you don't have those exposed charges, you're not going to get electricity being conducted. Does that make sense?
Yes.
Yes.
So electrolytes, again, are just going to be your charged, they're going to be charged particles in solution, okay? And so they're going to be used to pass an electrical charge through it. An electrode is just going to be conductors by which your electrons are able to pass through, or your electrical charges are able to enter and leave, okay? Electrolysis is that process of doing this, okay? Okay, so here we have a solution of potassium chloride that we put into water. So the potassium ion and the chloride ion separates. Potassium is positive charge, chlorine is, or the chloride is negative charge. And so these guys are going to be able to conduct electricity. The reason why they're able to conduct electricity is because the electrons are going to be able to flow through here. That's going to cause this electron to be attracted to this guy, this the potassium, right? Making it neutral. And then that electron then is going to be passed on to the next one. And then it's going to be passed on, and then that guy's going to be passed on to this one, and this guy's going to be attached to that positive pole, right? And so you're going to get conduction of electricity because of that passing on of things. Does that make sense?
Yeah.
And so at the end of the day, your electron is going to be able to flow through the solution and go back through the cycle. So it closes that loop, okay? So a strong electrolyte basically almost completely dissolves, or completely dissociates, or completely ionizes. Ionize basically means it forms its ions, okay? A weak electrolyte only dissolves a little bit or dissociates a little bit, okay? Or ionizes a little bit, okay? And a non-electrolyte doesn't ionize at all, okay? So it's completely neutral. So you're not going to have any electricity being conducted in that case. A strong electrolyte will conduct electricity very well. A weak electrolyte will conduct it poorly. Okay. So here, if we look at the a solution, right? So if we have sodium chloride, solid, right? So salt. If we add water, what happens when we add salt to water? Are you guys there?
It becomes buoyant.
You get salt
It becomes
water.
buoyant. Are you telling me that salt floats on top of water?
No, but the water itself becomes buoyant.
So you're
Salt
saying
dissolves
water,
into the water.
water floats on top of salt?
No, like if you put something in it, heavier items could float.
The salt dissolves into the water.
The salt dissolves into the water, right? Okay, so in this case, we have salt dissolving into the water. And the reason why it dissolves is because it breaks up that ionic bond. So that sodium is going to be interacting with the polar, the hydrogen, the polar parts of the hydrogen, and then the chlorine is going to be acting with the oxygen, okay? And I'll show you that image here in a second, okay? And the same thing happens in the case of the copper chloride. It's going to be able to dissolve in solution, and then you're going to get your ions formed, right? So water is kind of like a home wrecker. It breaks up that happy relationship between sodium chloride. It gets in between the two, separates. Okay, so here we have sodium chloride. This here represents the chlorine ion. And if you notice the white dots here, that represents your hydrogens. So your hydrogens are oriented towards your chlorine because your hydrogens are going to be what we call partially, when we talked about polarity. This guy's going to be partially positive. And this guy is going to be partially negative, the oxygen. So your partially positives are going to orient towards the negative charge, right? Because positive and negative attract, right? And then your oxygen is going to orient towards the sodium because it's positively charged. Does that make sense?
Yeah.
Okay. So literally you have water, like I said, being a home wrecker. It broke up sodium and chloride, or sodium chloride. So they're individuals now, they're single. Solo YOLO, right? Okay, so the same thing happens with the copper chloride. So in this case, we have your copper and your chloride oriented in this matrix. As soon as we add that copper chloride to solution, it's actually gonna, or copper 2 chloride into solution, it's gonna separate into its ions. And the same thing's gonna happen in that context. The oxygens are gonna orient towards the chloride. The oxygen is gonna orient towards the copper. And then the hydrogens are going to orient towards the chloride. Just got to fix it. Okay. Okay, write the dissolving equation for potassium sulfate. Okay, so in this case, you want to write the chemical equation for being dissolved, just like the one that was written before. So what am I going to do? Are you guys there?
Yeah, I was trying to process this.
Okay, so if I add water to potassium sulfate, what's going to happen? Is it an ionic compound? Is it a covalent compound? What do you think is going to happen to it?
It's going to break up.
It's going to break up. So we're going to get our potassium ion. What is the charge on potassium?
1.
Okay, so it's going to be potassium plus AQ. That AQ means in water. And there's going to be 2 of them because now they're broken up. Everybody's single, right? So they're able to separate to their ionic parts. And then we know that sulfate is a covalent polyatomic ion. What is the charge of sulfate?
2 minus.
2 minus. And that's going to be also aqueous. Okay, so this is an example of a dissolving equation, right? So we have that solid, we're going to be adding water, and then we're going to get these guys broken up into their ionic components. Piece of cake?
Yeah.
Okay, so write the ions present in the solution for calcium nitrate. So what 2 ions are going to be in a solution of calcium nitrate?
Ca2 plus.
Ca2 plus, and we want to put AQ to let us know it's in a solution. And
NO3 minus AQ.
simple. Don't overthink it because it's not too hard. It's just breaking up those charges, right? That plus and that minus. Okay. Now the same thing happens with acids. Now the thing about acids, if it's a simple acid, what you're going to do is get broken up into your hydronium ion, which is kind of like that H plus, AQ, and then your negative ion, right? We should say AQ. Don't yawn. It's not that boring.
My bad. I forgot to mute it.
Get up, stand up, scratch a little bit. Okay, so you're going to be breaking up into these 2 components. Now, H plus and H3, oops, O plus, they're the same thing. The only thing is that these guys are going to be equal to each other. They're essentially the same thing. Hydronium ion has just attached that proton that's been added. So what happens is that proton, when it separates from the acid, it grabs onto the first thing that it can grab on. That's one of the things that makes acids so strong, is because that H plus grabs onto what it can grab onto. And the first thing it grabs onto is water. So then it becomes H3O plus, okay? So that H plus is kind of clingy. And so it's like, oh, I need you, okay? So that's the same thing it does when it gets into your skin, right? The first thing it does is tries to grab onto something. So it grabs onto that part of your skin and starts messing up your skin. So if you spill acid on your skin, you get a chemical burn. Have you guys heard of that before?
Yeah.
Yeah.
Okay, so that's what happens with strong acids. So a strong acid dissociates completely, right, into its ionic parts. Okay, so then you're going to get the H3O plus, and you're going to get the Cl minus in the case of hydrochloric acid. In the case of nitric acid, the same thing is going to happen because these are strong acids, so they're going to dissociate completely. I swear I keep fixing this every year and it keeps screwing up. So here, these guys are polyprotic acids. So basically what happens is they'll lose that first hydrogen, and then they'll go off and lose the second hydrogen in the case of hydrogen sulfate. The sulfuric acid in the case of sulfuric acid. Okay, so it's able to lose that very first hydrogen, and then it'll lose that second hydrogen. So these guys are called polyprotic. spell it for you. Polyprotic acids. So meaning that they can lose more than one hydrogen or more than one proton. Okay. And these are carbon acids. Well, carbon acids really don't like to lose that hydrogen too often. They'll do a little bit. So they set up an equilibrium so that they'll have, in some cases, they'll keep that hydrogen. In other cases, they'll break down and that hydrogen ion will be released. Okay. So this is an example that both of them exist at the same time. So you still have a lot of the guys that are still connected, and you also have a little bit of the guys that are in solution. Does that make sense? Okay, so all carbon-based acids are weak acids. So carbon-containing acids are weak acids. They don't like to be ionized. They don't like to form the ions. I cannot wait to get back in class, because then I can look at your faces and say, okay, they got this or they don't got this. Okay, so what did I say about strong acids?
They're almost
Completely
completely aqueous.
Okay, they're almost completely dissociated in an aqueous solution. Okay, so when we talk about them being completely dissociated, we're going to be talking about our species. So we call them major species. Major species is the one that's the most abundant in your solution. Okay, so a strong acid is going to have ions as its major species. And then the minor species is the one that you have the less of, right? So the unionized molecule is going to be the minor species. Okay. And a weak acid is going to be just the opposite. Your major species is going to be your unionized molecule, and your minor species is going to be your ions. Okay. So here's an example. So in a strong acid, which is also a strong electrolyte, we have hydrogen chloride. So you can see all of the hydrogens, the chloride ions, are all dissociated from the hydrogen or the hydronium ion. Okay, and so you're just having ions in here. So this guy is able to conduct electricity, where in a weak acid, the majority of these guys are still intact. They're not ionized. So they're unionized, but you have one of them that is. So the majority of the things in here are unionized molecules, but you have one ionized molecules. So that's going to give you a weak electrical signal, right? And so your bulb, you know, it lights up just a little. Okay, do you guys get that?
Yeah.
Okay. Okay, so we're going to stop here and we'll pick this back up on Monday. So strong acids.
Correction, Tuesday.
Oh, sorry. But I know you guys like me so much that you want to come on Monday too, right?
I won't be there Monday.
Of course, we do.